Well, this is electric circuits course of second semester offered in spring 2020 textbook. I'm Dr. Khalid Emerson in the Department of Electrical Engineering, UET, Lahore. We are discussing signal waveforms, and this is the last lecture, means part 3. And in this part 3, we will discuss waveform partial descriptors. Partial descriptors are used to uh, describe or define a waveform. An equation or graph defines a waveform for all time. Equation or graph, it defines a waveform for all time. The value of waveform Vt or It at time t is called instantaneous value. The value of any function at any given time is known as instantaneous value. If one were to replace t with a particular time and evaluate the equation, one would obtain the value of the waveform for that particular time or instant. Uh, we often use parameters called partial descriptors that characterize important features of waveforms but don't give a complete description. Now there are the partial descriptors, they fall into two categories: temporal features, time related features, and amplitude features, means the amplitude related features. This is a sinusoidal waveform, and its amplitude is VA, and we can express it as VA sine omega naught t, where omega naught is determined due to this t naught, the time period. Temporal descriptors, time-related descriptors, they identify waveform attributes relative to time axis. For example, waveforms that repeat themselves at a fixed time interval is said to be periodic. This waveform, this is one cycle of the waveform, and the same cycle is repeated again and again and again. We have shown only the waveform for t equal to and greater than 0. It may be on the both sides for negative time as well. A signal is periodic if the value of the signal at any time is equal to the value of the signal at t plus t naught, where t naught is the time period. Say if we choose t here, and after t naught, this is t naught over here. So this value and this value, these two values are same. If these two values are same, this is Vt and this is Vt plus t naught. If these two values are same, then the waveform is periodic. Waveforms that are identically zero prior to some specified time are said to be causal. This is a new concept, but it is a simple concept. I will read it again. Waveforms that are identically zero prior to some specified time. So here in this waveform, the specified time is t equal to 0. I'm finding the laser. So before t equal to 0, it is identically 0. Identically 0. So this type of waveform is known as causal waveform. If it is 0 before this time, if it is 0, then it is also a causal waveform. A signal. Now, the formal definition of a causal signal or waveform is that a signal Vt is causal if there exists a value t such that Vt is 0 for all t greater than, for all t less than t, otherwise it is non-causal. Uh, it will, it is not very clear. I should have given you examples, but I will move further. We may discuss few examples. Causal waveforms play a central role in circuit analysis. When the input driving force is causal, driving force in electrical circuits may be a voltage source or a current source. If it is causal, the circuit response Yt, the response of the circuit or output of the circuit must also be causal. Means it will start after a specified time. That is, a physically realizable circuit cannot anticipate and respond to an input before it is applied. It means that if a signal is applied at xt, then response due to this input cannot appear before the time t. It will start appearing at t and onward. Causality uh, is an important temporal feature, time-related feature, but only a partial description of the waveform. These two waveforms are periodic waveforms. It repeats itself. If I start from here, so this is one cycle, this is next cycle, and this is next cycle. And similarly, this is also a periodic. Though its amplitude, all the time the amplitude of this signal is greater than zero, always greater than zero, but it is periodic. Now, the amplitude descriptors are peak to peak value represented by VPP. It is V maximum minus V minimum. So V maximum, it is self-explanatory. V maximum, the maximum value, and this is the V minimum value. Here, this is the V maximum, and this is V minimum. So peak to peak is V maximum minus V minimum. In this case, V minimum is negative. So say this is plus 1 and this is minus 9. Peak to peak value will be 1 minus 9. So peak to peak will be 10. So here, if this is 10 and this is 1 plus 10 plus 1, peak to peak will be 10 minus 1. Only peak value is the mod of V maximum. We consider maximum value and minimum value, and without signs. Mod means without sign. Maximum value, minimum value, and then we choose maximum of these two. Say for example, this is plus 1 and this is minus 9. So plus 1 over here, it is mod value is plus 1 minus 9, it will be 9. So we have two values, 1 and 9. So maximum of 1 and 9 is 9. So V peak. So then this will be the V peak. Here, this is the V peak. Again, partial descriptors, and this is an example. Peak to peak value, V maximum minus V minimum. V maximum is 4. V minimum is 10. So 4 minus 10, this is 14. And what is V peak? V peak is mod value of V maximum and mod value of V. So V maximum is 4. So mod of 4 is 4. V minimum is minus 10. Mod of minus 10 is 10. So 4 and 10, what is maximum of 4 and 10? It is 10. So this is the peak value. This is the peak value. And the time period, it is given over here. Otherwise, if it is not given, there should be markers on it, and in millisecond, and then we can find the time period from here. And f is 1 over t, omega is 2 pi f. We have discussed these before, and you all already know it due to college uh, physics and mathematics. Now, the mathematical description of this waveform. Mathematical description of this waveform is basically here uh, in a balanced sinusoidal waveform. If it is balanced, so this should be the origin over here. But as if this is the origin, which is now shifted to this, it means that this zero axis has been moved up over here, and this is reflected as -3. So it means 7 sine 418 minus 3. This is the mathematical description of this. If this zero axis over here, if it is moved here, so I will show you. If we move it here, if this is our time axis and this is the position of the time axis, then it means that this waveform is a sinusoidal waveform, and we will represent it as 7 sine 418.870 plus 3. So later we will call it amplitude shift. We have moved it up or we have moved it down. Again, this is another amplitude descriptor, average value. Average value is also known as DC component, and we compute average value due to this expression. It is 1 divided by t, an integral of v of x. So this is okay, is expressed in the generalized form vx and dx from t to t plus delta t. It means we integrate this signal for one time period. For one time, we can start it from here, end up over here, or if we start it from here, we should end up over here, or we can start from here, it should end up over here. So we should consider one complete cycle in it. Average value is also known as DC component, because DC signals are constant for all time. So we will have a constant value as a result of this expression, and we will discuss some examples. Now there is another amplitude descriptor which indicates AC component in the waveform. So in this waveform, the AC component is we will see what is the AC component in it. The AC component in it is the average value is 0. The average value is 0. How do we measure the AC component in it? It will be discussed in the following slide. So we have a voltage 5 minus coefficient of sine minus coefficient of sine minus, so here the frequency 2 pi 5000 2 pi, so this is twice this frequency and this is 3 times this frequency. We call it fundamental harmonic, and this is twice the fundamental harmonic and 3 times the fundamental harmonics. So in the whole expression or description of the voltage, so this part is constant, this part is constant, and this is known as DC component of this signal. Though the waveform of this signal is not shown, but from here, what is the constant value? This is the constant value. It remains same. However, there is say variations in it, sine, and this is sine, and the three components are known as AC components in it. Now, this is half wave sinusoid, half wave rectified. This is the output of a half wave rectifier. We have clipped or we have omitted the negative cycle and we have kept only positive cycle. We can omit positive cycle and we can keep the negative cycle. So we are considering only positive halves of this periodic waveform. What is T naught? This part is repeating itself. This part is repeating itself now over here. Therefore, the T naught from here to here is T naught, and this is half of the time period. V peak to peak. V peak to peak is V maximum minus V minimum. V maximum is VA, V minimum is 0, therefore it is VA, and V peak is also VA due to its nature. It's a half wave, so V peak to peak and V peak is. Now we compute the V average value. So as it is VA sine 2 pi t over T naught dt, you can call it omega naught t as well. You can express it omega naught t, but we have discussed this type of argument in the previous slides and previous lecture. So 1 over T naught 0 to T naught by 2. Why we are integrating it from 0 to T naught by 2? Because it is uh, it is non-zero from 0 to T naught by 2, and it is 0 from here to here. Therefore, this part is 0, and we integrate this function from 0 to T naught by 2. If we proceed further, if we perform this integration, we have VA divided by pi, and this is 0.318 times VA. So it means that if we have this, if this is the output, voltage output of a circuit, and we measure it with the DC voltmeter, it will measure 0.318 times VA. It means that if this peak value is 10, our DC voltmeter, which measures the DC component, it will measure 3.18 volts. Root mean square value. This value is a measure of average power carried by the signal. Average power carried, note that it is average power. The instantaneous power delivered to a resistor by a voltage. So this is V square divided by R. This is the average power delivered to a resistor by a voltage VT. Basically, it is Vi, and this Vi or V square over R or I square R. So here we have chosen it voltage square divided by R. The average power delivered to a resistor in time span T is defined as. So the average power, if we take, if this is the instantaneous value of the power is expressed in time domain over here, Pt, this is power, whatever this function may be. If we want to take its average value, what do? We integrate it for one cycle, and we divide it by its t, what is the time period. Now, the P average, uh, now we substitute, what is PT? We have defined this is the PT. This is the function of the PT, 1 divided by R V square, 1 divided by R V square. So this is the P average. What we have done, we have substituted this P in this uh, expression in order to compute average power. Now, if we consider the term inside the bracket as VRMS square and then divide by R, this is the average power delivered to a resistor. The unit of the bracketed term, the unit of the bracketed term uh, are volt squared. The square root of the term defines the amplitude partial descriptor VRMS. So this is known as VRMS. If we take the root mean square of this root, if we take square root of this, this will be known as RMS value. This part is known as RMS value, and it is expressed over here VRMS divided by R. So if the signal is AC, the voltage is AC, then we compute the P average as VRMS divided by V square of the RMS divided by RMS voltage divided by R. Again, V average of a pure sinusoidal waveform is 0. It is, if we consider, if you recall the mathematical expression in to compute the average value, it is 1 divided by t multiplied by integral of the function from 0 to t naught, or from any time to that time plus t naught for one cycle. So due to the integration, we actually compute the area under the curve. The area under the curve in positive side, it is this, the area under the curve in negative is this. So it is the average area in one cycle. So as these two areas are exactly same but opposite in polarity, we add these two and the average value is 0. However, if we compute the root mean square value, so this is using the expression of the root mean square. It is root and then mean and square. So what is the expression of this? It is VA sine omega naught t. So this is VA sine omega naught t. So we take square of this. So it becomes VA square and sine square, and we integrate it from 0 to t naught, and we end up over here, and finally it is 0.707 of the peak value. It means that if the peak value is 100 volt, it's of a sinusoidal waveform, the RMS value will be 70.7 volts. Now, if we measure the sinusoidal waveform, sinusoidal say voltage or AC voltage with the help of AC meter, it will measure the RMS value. The AC voltmeter measures RMS value and DC voltmeter measures DC value, average value. So we can compute the average value of any periodic waveform, and we can compute RMS value of any periodic waveform. This waveform is periodic. This part is repeated again and again. So this part we know what is the time period. We compute the area. So in order to compute the area, it is better if we have mathematical expression of this line, mathematical expression of this line. So the V average is VA divided by 2. If we compute V average, it is VA divided by 2, because this is 0 all the time. This waveform, the amplitude of this waveform is above this 0. So just compute the area. It is VA divided by 2. This plus this is the average value. RMS value, what is mathematical expression of this curve? So this is VAT divided by T naught. If you find the equation of this line, due to college physics, you are more familiar with the equation of a straight line, y is equal to mx plus c. So if you use this formula in order to find mathematical expression of this, it will be VAT divided by T naught. We take square of this, integrate it, divide by its time period, and then take square root. So finally it will be VA divided by square root 3, and it is 0.577. This is the RMS value. This average value and RMS value, it is different in this case and in the previous case as well. Now finding RMS values, there are several examples mentioned, given in the textbook. How we can find the average value of this? As everything is known over here, we find the area under the curve, which is like this. Under the cursor, area under the curve, we can find the area by adding this area. What is this area? this side is 15 to 30. 15 multiplied by 1, the area is 15. What is the width over here? 15 multiplied by 2, this is 30, and area under this, in this segment, this is the width is 15 and it is multiplied by 3. 15 multiplied by 3 is 45. 45 plus 30 plus 15, and divide by its time period. Divide by its time period. All only one cycle is shown. Only one cycle. So if we extend it further, it will be like this. The cycle will be repeated again and again. In this case, how to find average value? Compute the area, compute the area, compute the area, and divide it by T naught. So sorry, this only this part is repeated. Only the part, the repetition is we have this and this part. Only this part over here. So again, we have the same thing. So which is not shown over here. Uh, So compute the R. V average is equal to 1 divided by T naught. T naught is 4 milliseconds. This is very important. Unit of time is very important. Millisecond, second, microsecond, nanosecond. So mind this. Be careful about this. 1 divided by T naught and integral from 0 to 4 millisecond. And inside the integral, we will have 10 dt plus another integral minus 5 dt plus another integral from 4 to 5. So what I am saying is that the average of this, take the integral from 0 to 1 millisecond. 0 to 1 millisecond. It is not easy to write with the cursor. So average value, its average value, it is V average. V average is 1 divided by T, and inside the bracket, what is this? The function over here, 10. So this is 10 and dt. So again, the integral plus, this is for this part. And it is 2 to 3, it is 2 to 3 millisecond, and what is the value? It is minus 5 dt, and plus you can plus only this is 0, so it has no contribution in the V average, so it is 4 to 5 millisecond. So this is millisecond, 4 millisecond, 5 millisecond, and the value is 10. So it is 10 dt, and computed, you will have the average value. And next, there is another waveform. So in the textbook, there are many examples and end problems. Many examples are discussed and end problems are given. So this is again a periodic waveform. This part over here, this is periodic waveform. This is, sorry, this part is this part is repeated again and again. Therefore, the time period is from here to here. The time period is, this is second. The time period is 0.02 second. And I hope you should be able to find the expression of we have discussed a composite waveform over here, and this will be 4 exponential raised to the power minus t divided by tc, and you should be able to compute tc of this time constant. The time constant will be same for this second half, and the expression, you find the expression, mathematical expression of this. Again, the mathematical expression of this is 4 multiplied by 1 minus exponent raised to the power minus t divided by tc. See my previous slides. So integrated from 0 to 0.01 and then plus another integration for this function, and this function is 4e raised to the power minus t over tc, and integrated from 0 to this, and then uh, divide it by the time period from here to here. You will have average value, and if you can find the expression, mathematical representation of this and mathematical representation of this, you can compute the RMS value. See some solved examples in the textbook. Or for practice, you should be able to compute average RMS, and average RMS of all the waveforms shown. This is end of part 3 as well as end of chapter number 5, and you all are advised to attempt all end problems. Thank you.